Welcome, fellow chemists, to the first of 3 videos on the nomenclature of alkanes. You will be introduced to the basic alkanes here, their substituents, and the IUPAC naming system. Here is an example organic molecule along with its name. If you're wondering how that molecule ends up with that name, don't worry. The name is systematic, which means if we can understand it for one molecule, we can apply that to others. So what do we need to know? First, the position, usually denoted with numbers, of a substituent or functional group. Next, numerical prefixes like di, tri, or tetra indicate multiples of the same substituent or group. Then the name of group smaller than but attached to the parent, which is the name of the longest continuous chain of carbon atoms. Finally, the name of any functional groups are placed at the end of the name and will be preceded by their location. If you do not know what some of those terms mean yet, don't worry, we're only 47 seconds in. But I'm going to make a slight change to the molecule by removing the amine. That we have a new name should not be too shocking, but you may notice we now have no need for the additional location and the functional group suffix. Those of you with really sharp eyes also notice the location of the 2 methyl groups changed. And this is a great example of one of 3 concepts we want to keep in mind as we go forward. 1. We list the substituents alphabetically. 2. We want our location values to be as small as possible. And 3. There might be a common name used instead. So why use common names? Well, maybe the compound is used very often, or the IUPAC name is ridiculous like the one you see on the screen. Do you know what it is? It's caffeine. But before we can name a complex molecule like caffeine, we will start with the small, simple molecules first. Alkanes are named based on the number of carbons they contain. Cycloalkanes, coming in part 2, and alkyl substituents have the same number of carbons but fewer hydrogens. The names of the first 4, meth, eth, prop, and bute, do not seem to line up with the number of carbons, but after that, the prefixes used to note the number of carbons should be familiar to you. They are the same you learn in geometry for naming polygons or in general chemistry for naming binary molecular compounds. For simplicity, these examples will end after 10 carbons, but it does extend beyond that. I recommend familiarizing yourself with these prefixes because you're about to use them a lot. The first rule of nomenclature is to identify the parent hydrocarbon, which is determined by the longest continuous chain of carbon atoms on the molecule. While sometimes it is obvious where this longest chain is, a good habit to start with is trying all possibilities just to be sure. We can see the paths being traced on this molecule on the screen, but we need to find the longest one possible. The final path results in a continuous chain 9 carbons long, and using the prefixes we just saw, we can identify this parent alkane as nonane. The alkyl substituent is attached to the parent somewhere. Not only do we need to know the identity of the substituent, which we determine by counting its carbons, we need to know where it is located. For this example, we count from one end of the chain to the location of the methyl substituent. We want this number to be as small as possible, so after counting from the left and getting a 6, we try from the right too. We pick the smaller of the numbers which we will use in the name. For this molecule, the methyl group is located on carbon 4, and the parent, which we saw earlier, is nonane. So in order to name this molecule, all we have to do is put that information together, starting with the substituent, and we get 4-methylnonane. If there are multiple substituents, ensure the locations are numbered as low as possible and that they are cited not by position order, but alphabetically. In the case of identical substituents, utilize the appropriate numerical prefix to indicate how many there are. As will be the case from here on out, pause the video and give it a go naming the molecule on the screen before we start. When first starting to name organic molecules, check all possibilities, but I imagine most of you already know where the longest chain is on this molecule and its name. After identifying the parent, you now move on to any substituents the molecule might have. In this case, there are 2. After identifying those substituents, if they happen to be identical, utilize the appropriate numerical prefix indicating how many there are. When that is done, you need to identify the locations of these substituents. And it is possible a quick glance is enough to determine which side you should count from. However, check both directions and choose the one that results in the smallest possible number. In this case, numbering from the right gives us a 2 and 4, so we pick that option. Now that we have identified everything we could for this molecule, we can put it all together to develop the name, which is 2,4-dimethylheptane. If numbering in both directions results in a tie, move to the next substituent. Whichever direction results in the lowest number now is the one you choose. I will let you pause and ponder a bit on that rule and how you would use it to name this molecule. You still need to identify the parent hydrocarbon, as well as the name of any substituents the molecule has, and if necessary, numerical prefixes. You will notice that I have ordered the substituents on this molecule alphabetically, as that reflects how we will need to name it. Finding the locations is the same as before, and we will want to check both directions. We finally have an example with 3 locations, but the method is still the same as before. In this case, both directions results in a tie for the lowest possible number, a 3. We will need to break this tie, and in order to do that, we move on to the next lowest number we have from either side. Clearly, this is a 4, and we only get that if we number from the left. So we use the numbers 3, 4, and 7 for the locations of our substituents. And putting together everything we have, we generate the name 7-ethyl 3,4-dimethyl nonane. If there is a tie that cannot be broken by using Rule 4, then whatever substituent is cited first gets the lowest number. This essentially means whichever substituent is first alphabetically will get the lower number, as it must be first in the name. So keep that in mind while you try to name this molecule. In this case, the 2 substituents on the octane parent are, from left to right, propyl and methyl. The numbering from the left of this molecule is going to give us a 4 and then a 5. If the rule description did not already give away what is going to happen here, if we number from the right, we also get a 4 and a 5. So this gives us 2 sets of possible locations with the exact same numbers, a 4 for the propyl and a 5 for the methyl, or a 5 for the propyl and a 4 for the methyl. So using these sets of numbers, we generate 2 possible names for the molecule: 5-methyl, 4-propyl, octane, or, by switching the numbers, 4-methyl, 5-propyl, octane. We use the alphabet to break the tie, and since M is before P, the correct name is 4-methyl, 5-propyl, octane. If there is a tie in parent length, choose the parent that has the greatest number of substituents. This can be quite tricky depending on the molecule, so it may take a few examples for you to get comfortable with. In this case, the straight left to right path on this molecule only has 1 substituent. However, if we take a winding path from left to right, we actually find 3 substituents on this molecule, all in blue. So this path that has the 3 substituents is the one we must consider the parent. Armed with this information, try naming the molecule now. We already know that the parent is octane, and the substituents get named as they always have. Since we have 2 methyl groups, we need a numerical prefix associated with it. In this case, it's going to be di. As for the numbering, I'm only going to go from the correct direction. So we get the first methyl on carbon 2, the second methyl on carbon 3, and our propyl group is on carbon 4. So we put all of that information together and get the name 2,3-dimethyl 4-propyl octane. If there is a smaller chain attached to a larger chain, it is named with the same rules with the exception that carbon number 1 is where it attaches to the larger parent. While this certainly makes more sense to see in action than read on a screen, try it for yourself and see what name you come up with for the molecule on the screen now. In this example, the parent is actually 11 carbons in length, which is known as undecane. The numbering is from the correct direction, and on the 4th carbon there is a methyl. And on carbon number 6, there is our smaller chain substituent. The chain is composed of a parent butyl group, and on the 2nd carbon of that butyl group, there is another methyl. I have kept the small chain information inside green boxes. Since the methyls are not on the same parent, we do not use the numerical prefix di in this case. Once you have everything identified, putting the name together is the same as all the others. However, when you reach the small chain, you put it inside parentheses. The full name for this molecule is 4-methyl-6,2-methyl-butyl undecane. To summarize the naming rules, First, find the longest continuous chain of carbon atoms. You then name substituents before the parent hydrocarbon and give them the lowest possible location number. If there are multiple substituents, cite them alphabetically and use numerical prefixes if necessary. In the case of a location tie, move to the next substituent to determine the smallest possible number. If the tie cannot be broken, give the lower number to the substituent named first. If there is a tie in parent length, choose the path with the greatest number of substituents. And finally, if there is a smaller chain on a larger chain, it attaches to the parent at carbon number 1, and it is otherwise named using the same rules. In part 2, we will continue naming alkanes and venture into cycloalkanes, alkyl halides, and ethers. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. I would like to use this moment not only to put a link to my previous video on radical substitution reactions on the screen, but to also recommend a couple of excellent science channels. First, Periodic Videos by Brady Haran, which is clearly linked to the chemistry content you will find on this channel, and Steve Mould, who not only posts chemistry content from time to time, but also manages to write science books appropriate for young kids, which may be an excellent holiday gift idea. You will find links to their channels and websites in the description. Please feel free to get in touch with me via email, social media, or if you would like, make a request in the comments.